Dear GATE aspirants, welcome to VEDA GATE Academy. In this session, let us go with KVL. What is KVL, dears? Kirchhoff's voltage law. Many will feel network subject as difficult and a bit confusing. Reason they are not perfect with K laws. Let us clearly understand what is this KVL. Shall we start, dears? Yes. What is KVL, sir? Kirchhoff's voltage law. Where it is defined? It is defined in a closed path. KVL is defined in a closed path. The closed path can be a mesh or loop. Fine, sir. What is the definition of KVL? Definition of KVL. Algebraic sum of voltages in a closed path equals to 0. I repeat the statement. Algebraic sum of voltages in a closed path equals to 0. This is what the statement given by KVL. Fine, sir. Right. Now let us clearly understand what is the sign convention of this KVL. Sir, if you are perfect with my sign convention, open challenge, any textbook, any problem, easily you can write the equations. Easily you can solve the problems. Fine, sir. Please be perfect with my KVL sign convention. Whatever the sign convention you know earlier, please leave it. Follow the sign convention. You will feel the advantage. You will see the advantage. Done, sir? Right. Let us write the sign convention of KVL. Sign convention which I follow for RLC elements. Sign convention. Fine, sir? Right. Suppose if we have a resistor, suppose if this is the branch current, and this is your direction of travel, say. Sir, what is this direction of travel? Brother, just I said, KVL is defined in a closed path. In a closed path, we can move like this or we can move like this. Yes or no? Clockwise and anti-clockwise. So this direction of travel represents either clockwise direction of travel or anti-clockwise direction of travel. Fine, sir? Right. Here this is a resistor R. Now please observe. Branch current, direction of travel. Both are in same direction or opposite direction? I am repeating my statement. Branch current and direction of travel. Here both are in same direction. Voltage drop across resistor we write as plus I into R. Again I am repeating, sir. Branch current, direction of travel. Both are in same direction. Voltage drop across resistor we write as plus I into R. Next. One more case I am taking here. Resistor R. Let me slide this. Resistor R. And this is branch current I. Suppose direction of travel is like this, say. Direction of travel is like this, say. Now tell me, sir. Branch current, direction of travel. Both are in same direction or opposite direction? Both are in opposite direction. Voltage drop across resistor we write as minus I into R. Simple statement, sir. If branch current, direction of travel are in same direction, voltage drop across resistor we write as plus I into R. Suppose if branch current and direction of travel are in opposite direction, voltage drop across resistor we write as minus I into R. Any difficulty, dears? Any difficulty? We don't have any difficulty in this. Yes or no? Right. Next, let me take some examples here. I'm taking a 2 ohm resistor, whatever the combinations that are possible. Let's take all the combinations, sir. Some 2 amps. Suppose direction of travel is like this, say. Next, the same 2 ohm resistor with a current of 2 amperes. Direction of travel anti-clockwise, say. What is the other combination, sir? 2 ohm resistor, but current coming like this, say. Direction of travel is clockwise, say. Direction of travel is clockwise. The same 2 ohm resistor, direction of travel anti-clockwise. Hope now we have all the 4 combinations with us. All the 4 combinations, sir. Here current flowing right to left. Here current flowing, here current flowing left to right. Here current flowing left to right. Here current flowing right to left. Here also current flowing right to left. Clockwise, anti-clockwise, direction of travels. All the 4 combinations are completed. Yes or no? Right. Now tell me, sir. If branch current, direction of travel on same direction, voltage drop across resistor we write as plus I into R, plus 4 volts. Whereas here, branch current direction of travel are in opposite direction. Voltage drop across resistor we write as minus I into R. Sir, here you feel it as a bit simple, but when you get into problems and all, you feel the real advantage, dears. So here's just writing plus 4 volts or minus 4 volts. What advantage we are getting here? Wait, dears. Once we enter into problems, complex circuits and all, even in transients, I will use this. Okay? In transients, I will find the capacitor voltage without putting pins here. To get that advantage, you have to listen this. Done? Right. Here, branch current direction of travel. Both are in same direction or opposite direction? Opposite direction. We write as minus 4 volts. Branch current direction of travel. Both are in same direction. We write as plus 4 volts. Any difficulty? Yes. We don't have any difficulty. Yes or no? Right. But one interesting point here. You tell me, are we considering any polarities of the resistor here? We are least bothered about polarities of the resistor. We write here one important note statement, which is don't consider polarities of R. Very, very important statement here. Do not consider polarities of R. Do not consider polarities of R. Very, very important statement. Here not given, sir. Though examiner give those polarities, let us not consider those polarities. Fine, sir? Right. Now, let us go with sign convention for the sources. Sign convention for sources. Come on, engineers. What sources we have? Voltage source as well as current source. Voltage source as well as current source. I am taking one ideal voltage source here. Even this is one ideal voltage source. Let us take one ideal current source. Ideal current source I. Yes, ideal current source I. I am putting some so on here. Reason, so now please. Every voltage source will be having current. Please remember this point. Every voltage source will be having current. Once load is connected, some current will be drawn. Similarly, across every current source, we will be having voltage. In every voltage source, will be having current. Similarly, across every current source, will be having what? Voltage. Across every current source, will be having voltage. As said earlier, KVL is defined for a closed path. In the closed path, we will be having the direction of travel. Yes, suppose here, direction of travel is from top to bottom, say. Suppose here, direction of travel is from bottom to top, say. Here again, top to bottom. Here again, bottom to top, say. Fine, sir? Yes. Now you tell me, in the direction of travel, irrespective of branch current, you are entering at what polarity, sir? You are entering at positive polarity. Please mark plus V. Again, I am repeating. Suppose here, my direction of travel is from top to bottom. Okay? Irrespective of this branch current direction, you are entering at what polarity? You are entering at positive polarity. Yes or no? Yes. That's why I am putting plus V here. Next. Here, direction of travel is from bottom to top. Irrespective of branch current direction, you are entering at what polarity? Negative polarity. Please mark minus V. Next. Let me slide this. Here, in the direction of travel for current source, irrespective of source current direction, you are entering at what polarity, sir? Positive polarity. Please mark plus V. Suppose here, in the direction of travel, irrespective of source current, you are entering at what polarity, sir? Negative polarity. Please mark minus V. Please mark minus V. Any difficulty here? Coming to sources, in the direction of travel, at whatever the polarity you are entering, simply mark that polarity. Here we are not considering one thing. What is that? Don't consider, please, very, very important statement. Don't consider current direction in the source. Current direction in the source. If you note this, very, very important point, yes. If you note this, yes, easily we can write the equations. Done, sir? Sir, why you kept so on here? Why you kept so on? Let me use black pen. Yes. Here many combinations possible, sir. Here these polarities can be reversed. Here current direction can be reversed, or voltage polarities can be reversed. Many combinations are possible. For all the combination, whatever the sign convention we have learned, that is 100% valid. 100% this sign convention is true for any of the combination DS. Fine. Now shall we go with one circuit and write the Kvl equation? Shall we? Yes. Let me slide this. Let us take one closed path and write the Kvl equation by looking into the sign convention what we have derived or written. I am taking a simple circuit, sir. Simple circuit. Single mesh, voltage source V, R1 and R2. Come on, engineers. What current we discuss? Conventional current or electron current? We always go with the conventional current. Conventional current flows from what terminal to what terminal? Positive to negative. So current comes out of the source. Current flows like this. Current comes like this and enters negative terminal of the supply. Now, sir, now the real story starts. Come on, tell me. What direction of travel you want to take? You can take any direction of travel, DS. I am taking here clockwise direction of travel. Sir, what happens if I take anti-clockwise direction of travel? Please wait for some time. I will also take anti-clockwise direction of travel. Done. Tell me, in the direction of travel, you are entering at what polarity, sir? Positive polarity or negative polarity? You are entering at negative polarity. Let me write here minus V. Next, tell me, direction of travel branch current. Both are in same direction or opposite direction? Both are in same direction. I am writing here plus I into R1. Next, direction of travel branch current. Both are in same direction or opposite direction? Both are in same direction. Here we write as plus I into R2. As per the definition given by the KVL, algebraic sum of voltages in a closed path equals to 0. From here what we write, sir? V equals to IR1 plus IR2. Now doubt comes for students. Sir, I want to take anti-clockwise direction of travel. Yes, let us take anti-clockwise direction of travel. Suppose my direction of travel is like this, say. Now you tell me, direction of travel branch current. Both are in same direction or opposite direction, sir? Both are in opposite direction. What do you write here? Minus I into R2. Next, direction of travel branch current. Both are in same direction or opposite direction? Both are in opposite direction. What do you write here? Minus IR1. Next, direction of travel entering at what polarity, sir? Positive polarity. It is plus V equals to 0. Come on, sir. Now you tell me, this equation, both equations same or different? They are same, sir. Take minus common from this, you get this. Or take minus common from this, you will get this. From this, what I can write, sir? Can I write V as IR1 plus IR2? Come on, engineers. Yes, we can write V as IR1 plus IR2. Now tell me, writing KVL equations, easy or difficult? Sir, you have taken a single circuit and you are explaining. Even we are feeling it as easy. Please take some big circuit and explain us. Find yes. Some used to ask us, sir, please take some big circuit and explain us. Done. So before going to that, whatever the first statement we have learned, algebraic sum of voltage in a closed path equals to 0. The very first statement given by KVL. For your college exam sake and all, it is useful, sir. Whereas for the competitive exams, the statement which we are using, if you follow this, it takes a lot of time. It kills a lot of time, dears. Competitive exam, we have to save the time or we have to shave the time? We have to save the time. Fine. Let me give the second statement of KVL. What is that second statement of KVL? Please know, sir. Very, very important. Taking the same circuit, and I want to use or start using second statement of KVL. Whatever the statement I am giving now, it's a golden statement. Very, very important statement. Follow this statement. Easily you can write the equations. Not only the equations, even Thevenin's voltage, fully charged capacitor voltage, everything you can write in seconds. Done, sir. Giving that equation now. Giving that second statement of KVL now. Very important statement. See, what is the statement? Any voltage value equals to, start at positive, go up to negative, travel around the closed path, in which you know the voltages. I am not writing the statement here. Since it's a demo class, I am not writing the statement here. Done. Right. Any voltage value equals to start at positive, go up to negative, travel around the closed path in which you know the voltages. I'll clearly explain here. By the end of this class, I myself will use almost 20 plus times this statement. I will use this statement for 20 plus times for sure. Done? Right. So what is the statement? Any voltage value equals to, yes, V equals to, start at positive. Okay, we have to start from here. Go up to negative. Go up to negative. Travel around the closed path. See, I'm using travel around the closed path in which you know the voltages. In which you know the voltages. Sir, why you are using the word travel around the closed path? If I don't use that word, many will say, sir, started positive, go to negative means, sir, that is over. They are starting at positive, they are coming up to negative and they are saying it as over. Yes or no? Right. So, started positive, go up to negative, travel around the closed path. First, tell me, sir, how current comes? Current comes from positive terminal. Yes, current comes like this and enters negative terminal of the supply. Come on, sir. Now tell me, please. This is the direction of travel. Direction of travel, branch current, same or opposite? They are same. So, what right here? Plus I into R1. Next, direction of travel, branch current, same or opposite? Same. What you write, sir? Plus I into R2. Plus I into R2. Now tell me, this equation, the equation which you got earlier, both are same or different? This equation, same or not? They are same. No doubt comes for student. Sir, what difference is there between the earlier equation or earlier procedure and this procedure? Just you're writing voltage rise equals to voltage drops. That's it, na, sir? Sir, you're writing here voltage rise equal to voltage drops. That's it, na, sir? Note yes. I'm not using the statement. If at all that is the statement, I myself will give the statement, na? Voltage rise equal to voltage drops. So, here please observe, many will feel here a voltage rise as voltage drop, which is not true. I'm not using that class. But it is appearing like this. If the circuit is complex, you can't find where is the voltage rise and where is the voltage drop. Why? Because even some scenarios, sources do absorb power to satisfy K loss. Sources do absorb power to satisfy K loss. Okay? Right. Sir, let us take some big circuit and explain this statement. STS. Let us go into that. Sir, taking only one mesh and explaining, we are not satisfied. Take one more mesh. Yes, yes. Taking one more mesh. Is it sufficient? No, sir. Please take one more mesh. Taking one more mesh. Is it okay for you? No, sir. Please take one more mesh. One more closed path, sir. One more closed path. Closed path sufficient? No, sir. Please extend further. Closed path sufficient? No, sir. Please extend further. Yes. Closed path fine? Fine, yes. Let us take some arbitrary values, dear. This has 100 volts plus minus 65 volts plus minus 10 volts. Taking some arbitrary values, 15 volts plus minus 105 volts plus minus, take some 30 volts here, some 30 volts plus minus 25 volts, arbitrary values, 35 volts plus minus 55 volts and plus minus 10 volts. Sir, I can say this structure as my heart. If you analyze this structure, if you understand this structure with the second statement of KVL which I told you, yes, I can say networks is easy, sir. This structure is my heart. Giving this much intention or giving this much impression on the circuit. Reason? Yes, DS, follow this for other 15 to 20 minutes. You really understand why the structure is that much important. Done, sir? Right. Sir, I am telling only one statement. Entire network subject, you calculate only voltage and current. Entire network subject, you calculate only voltage and current. Suppose, sir, the branch is like this. What are the possible current directions, sir? Either right side or left side. Suppose the branch is like this. What are the possible current directions? Either downwards or upwards. Over. Based on position of the branch, you can clearly give the direction of the current. 50% possibility is there. Next, suppose the branch is like this. What are the possible voltage polarities? Either plus, minus or minus plus. Suppose the branch is like this. What are the possible voltage polarities, sir? Either plus, minus or minus plus. Here, my intention, I want to calculate these branch voltages. Please don't say, sir, all are short circuit branches. That's why the voltages are zero. Here we have resistors, dears. Resistors. All the resistors, some sources and some resistors. Okay. Right. Now let us start finding with this branch voltage. Fine, sir. Arbitrarily, I am putting two polarities here. I am putting plus here and I am putting minus here. Putting plus and minus. Let us take this branch voltage as some Vx. I want to find this branch voltage ds. Okay. Yes, please repeat the statement which I have given you earlier, the golden statement. Started positive. Okay, we have to start from positive. Go up to negative. Okay, we have to enter this negative terminal. Travel around the closed path in which you know the voltages. Travel around the closed path in which you know the voltages. Yes, sir. Sir, I want to travel like this. Do I know any voltage of this branch? I don't know. Means I should not go in this direction. Next, can I go like this? Yes, I know this branch voltage. Or can I go like this? No, I don't know this branch voltage. Can I go like this? I don't know this branch voltage. Can I go like this? I don't know this branch voltage. Yes or no? Finally, I can't go in this direction. Clear? Right. Can I start like this? Yes. Can I go like this? Yes. Can I go like this? Yes. 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 Can I go like this? Let me slide this. Hope it's visible to you. Yes. Can I go like this, sir? Can I go like this? No, I don't know this voltage. I can't go like this. Can I get down like this? I know this branch voltage, but do I know this voltage? No, I can't go. Even this is not possible. Can I get down like this? No, it is not possible. Even many got the answers. Many know answer of Vx. Okay, please wait. Please understand why. Because why I am explaining this, I have reason. I am linking this with the transients. I am linking this with Thevenin's theorem. Please understand. Please wait, yes, sir. Fine. Can I get down like this? No. Or only one option. What is the option, sir? I can get down like this. Now you tell me, in the direction of travel, Vx, you are entering at what polarity, sir? You are entering at what polarity? Come on. Direction of travel, you are entering at negative polarity. How much? Minus 100. Next, direction of travel. Direction of travel, you are entering at what polarity? Plus 65. Minus 100 plus 65. What is the value, dears? Minus 35 volts. Minus 35 volts. Come on, sir. Tell me. Voltage value we got positive or negative? Voltage value we got positive or negative? Voltage value we got negative. Yes. We don't like negative values. We want positive values. Means what you have to do, sir? Reverse the polarities. You will be getting positive value. Reverse the polarities. You will be getting positive value. Yes or no? Yes. So here I want to show, even by taking a reverse polarities, I want to prove the value as plus 35 volts. Then we get one conclusion. Let us arbitrarily take two polarities, plus and minus. So what is our statement? Started positive, go up to negative, travel around the closed path in which you know the voltages. Can I go like this? No, sir, I can't go like this. Reason, yes, I don't know this branch voltage. Can I go like this? Yes. Can I go like this? Yes. Can I go like this? Yes. Can I go like this? No, not possible. Can I go like this? Not possible. Can I get down like this? Not possible. Can I get down like this? Not possible. Why not possible, sir? Why? Because we don't know those branch voltages. Getting the point, please? Yes. So, in whatever the way we got earlier, let us go in the same way to find the value of Vx. Come on, engineers, tell me. Direction of travel. Entering at what polarity, sir? Negative polarity. Means what we write? Let me compress this. Yes. Hope it's visible to you, DS. So, I am entering at what polarity, sir? Vy. Let us call this as some Vy. Vy as entering at what polarity? Minus polarity. Minus 65 plus direction of travel. Entering at what polarity, sir? Plus 100. What is the value of Vy, dears? It is 35 volts. Got positive value or not? In future, will you get any doubts, sir? Sir, I want to find voltage across an element. What polarities I have to take? Take any polarities, bhaiya. Whether it's plus minus or minus plus, no problem. If you are taking plus minus, if you are getting positive value, assumed polarities are correct. Suppose if you are getting negative value, reverse polarities are correct. If you are getting negative value, reverse polarities are correct. But please don't get the doubt. What polarities has to be taken? No. Clear, sir? Right. Sir, if you do like this, it takes a lot of time now, sir. Yes. So, in short here, what is our statement? Started positive, go up to negative, travel around the closed path in which you know the voltages. Please don't select the path in which you don't know the voltages. Fine. Sir, now I will find the other branch voltages a bit faster. To reduce the clumsiness, I want to erase this direction of travels. Okay. Direction of travel we should not draw, sir. Direction of travel we have to view clockwise or anti-clockwise. Just view this. Easily you will be getting the answer. For this, I am erasing the direction of travels. I want to make the circuit ready available with us. So that I am erasing this. Erasing this black. Erasing this part, sir. Yes. Hope the circuit is ready for you. Yes. The statement, sir, which we are going to use in what the way which we are going to write the equations. Very, very important. I am erasing all this. Just follow this. How fastly we write the voltage. Now please understand. Now I want to expand this. Yes. Hope it's visible to you, DS. Yes. From now, the second statement of Kvl which we have learned, that I will be using here. See how fastly we write the voltages. Sir, I want to find this branch voltage. Arbitrarily, I am putting two polarities. Even I don't know whether these polarities are true or not. Start at positive, go to negative following Kvl sign convention. What is voltage, sir? Minus 65 plus 100. What is this value, dears? 35 volts. Hope it's visible to you, sir. 3 is visible to you. Yes. It is 35 volts. Clear? Next, I want to find this voltage. Arbitrarily, I am putting two polarities here. Arbitrarily two polarities. Start at positive, go to negative following Kvl sign convention. Can I go in this diagonal? No, not possible. Can I go like this? Yes. Can I go like this? Yes. Can I get down like this? No, not possible. Can I go like this? Yes. Can I go like this? Not possible. Next, can I come like this? Yes. Can I go like this? Yes. This triangle is perfectly suitable to calculate this branch voltage. Come on, engineers. What are the values, sir? Entering it, what it is? Plus 35 plus 30. What is this value here? 65 volts. 65 volts. Easy or not? Next, I want to find this branch voltage. Putting plus here, minus here. Start at positive, go to negative. Can I go like this? No, not possible. Can I go like this? Yes. Can I come like this? Yes. Can I go like this? Yes. One way. Other way. Next. Can I go like this? Yes. Can I come like this? Yes. Can I go like this? Yes. Now you tell me what way you want me to prefer. Square plus triangular path or only square path? Only square path is sufficient. Now I am adding one more word to my statement, to my golden statement. What is that? Start at positive. Go up to negative. Travel around the shortest closed path in which you know the voltages. Travel around the shortest closed path is important, dears. Very, very important. Get it? What's the point? Yes. Let us take the shortest closed path. Minus 105 plus 65 plus 65. Plus 65 plus 65, 130. 130 minus 105, it is simply 25 volts. Now doubt comes for the student. Sir, all the time how you can get the positive voltages? Okay. For your sake, let me take positive here. Let me take negative here. Okay. Start at positive, go to negative following Kvl sign condition. Come on. Come like this. Plus 25, entering it. Minus 65. What is the value, sir? It is minus 40 volts. Now what I do? Reverse the polarities and put positive voltage. I am putting reverse polarities, sir. Putting here plus, putting here minus. I am getting 40 volts. Got it, sir? Now this perfect square is over. Now for this square, we know all the branch voltages. Yes or no? Done. Now let's go with calculating the square voltages. Now DS, here, please start thinking before putting polarities itself. Since we want positive value, before putting polarities itself, please start thinking. Suppose if you put plus here, you will go like this. Minus 35, minus 10. You are getting negative voltage. Since you want positive voltage, what do you have to do, sir? Plus here, minus here. Start at positive. Go up to negative. Travel around the shortest closed path in which you know the voltage. Come on, engineers. What is this value, sir? Plus 10 plus 35. What is this value, please? 45 volts. Next, I want this branch voltage. If you put plus here, minus 55 plus 45. Getting negative voltage. Put plus here, put minus here. Minus 45 plus 55. What is the value, sir? 10 volts. What is the point? Next, I am putting polarities here. Put plus here, put minus here. Start at positive, go to negative. How much? minus 15 plus 55. What is the value, dears? 40 volts. What is the value, sir? 40 volts. Next, put plus here, put minus here. Minus 25 plus 40. What is this value, sir? 15 volts. Now this complete rectangle is over. Yes or no? Complete rectangle is over. Now let us go in calculating these branch voltages. Sir, arbitrarily two polarities. Arbitrarily two polarities. Plus and minus. Minus 10 plus 10. What is the value, sir? 0 volts. Minus 10 plus 10. What is the value? 0 volts. Next, arbitrarily two polarities. Plus and minus. Minus 15 plus 30. Come on. Minus 15 plus 30. What is the value, sir? Plus 15 volts. Plus 15 volts. Next, I want this branch voltage. Plus and minus. Minus 0 plus 15. What is the value here, sir? Plus 15 volts. Now, please cross check for this closed path whether the Kvl is satisfied or not. 15 equals to minus 10 plus 10 plus 15. Minus 10 plus 10 gets cancelled. 15 equals to 15. Perfectly Kvl is satisfied for this mesh. Done, dears? Right. Let me erase this part. Let me erase this. Yes. Now let us go in calculating other branch voltage. Come on, sir. Tell me what is this branch voltage. Put plus here, minus here. Plus 30 minus 25. What is this value, sir? Plus 5 volts. I want this branch voltage. Plus 30 plus 5. How much? 35 volts. So these are what the branch voltage is. Sir, the answers which we got, they are correct or not, how we can cross check. Please write Kvl for the outermost closed path. Please write Kvl for the outermost closed path and verify, dears. Come on, tell me, sir. Come on, tell me what is the equation that you will be getting. Let me compress this. Hope it's visible to you, dears. Yes. Now tell me, what is this voltage? 100 equals to, come on, fast. 100 equals to 105 minus 15 plus 10 plus 35 plus 10 plus 15 minus 25 minus 35 minus 35. 105 minus 15, 90, 90 plus 10, 100, 100 plus 35, 135, 135 plus 10, 145, 145 plus 15, 160, 160 minus 25, 135, 135 minus 35, 100, 100 equals to 100. Kvl perfectly satisfied. Kvl perfectly satisfied. Sir, in what way you are going to link this with the Thevenin's voltage? So, notice, now I am taking some numbers here. Some numbers. Let me erase this for clarity purpose. Yes. Let me erase this. Hope it's clear to you, dears. Right. Now, I am putting some names here. Let us take as some A. Let us take as some B, C, D, E, F, Z, H, I, J, K and L. K and L. Addition's over. Now I'm making you learn alphabets. Okay? Right. Come on, sir. Sir, what way you are going to link? Come on, you tell me, sir, everybody. What is VAB branch voltage? If anyone asks you VAB branch voltage, whether it is a branch voltage or a Thevenin's voltage or a capacitor open circuit voltage, what is the procedure we follow? Start at A, go to B, following KVL sign convention. So you tell me, if you start at A, go to B, following KVL sign convention, what is this branch voltage? Come on, right here, sir. What is the value? Plus 105 volts. If I ask you, what is VAZ? Start at A, go to Z, following KVL sign convention. Any possibility? You come like this. 105 plus 25. How much? 110 plus 20. 130 volts. Or you come like this. Plus 65 plus 65. How much? The same 130 volts. If anyone asks you, what is VAZ? What is your answer? Start at A, go to J. Start at A, go to J, following KVL sign convention. Come on, sir. Come on, tell me. How much? Plus 65 plus 65. 130, 130 plus 5. What is the answer? Plus 35 volts. 135 volts. This is how we calculate, sir. Suppose if anyone asks, what is VDF? What is the answer? Plus 35 plus 10. What is VCK? Plus 55 plus 15. What is VCJ? How much? Plus 55 plus 15 minus 25. Any branch voltage you can calculate now, sir. Started that point. Started A, go to Z following KVL sign convention. Or started A, go to Z following KVL sign convention. Travel around the path in which you know the voltages. Come on, sir. Hope you got the point. What is VHF? Started H, go to F following KVL sign convention. Plus 65 plus 15. Hope you got the point. What is VEI? Shortest path you prefer? Yes. Plus 10, minus 15 and minus 30. Plus 10, minus 15, minus 30. Like this, sir. Like this, you can calculate all the branch voltage. Yes or no? All the branch voltage can be calculated with the help of second statement of KVL. What is Thevenin's voltage, sir? How you find Thevenin's voltage? We open circuit the branch, put some A and B. Started A, go to B following KVL sign convention. Hope you got the point. Next, now I am introducing one more statement. KVL third statement. KVL third statement, sir. I can say it's like a diamond statement. Really it is. Diamond statement. KVL third statement is useful for finding the node voltages. KVL second statement is useful for finding the branch voltages. Getting the point, please? KVL second statement for branch voltages. KVL third statement is for finding the node voltages. Let us take some node voltage, sir. Right. For finding node voltage, one point is there. One important point. Node voltage is defined with respect to reference point. Node voltage is defined with respect to reference point. Without reference point, writing node voltage is meaningless. Without reference point, writing node voltage is meaningless. Let us take some reference point. I am using green color pen. I am taking J as reference point. Okay. Now you tell me, what is node voltage VA? Sir, what is KVL third statement, sir? Okay. VA is nothing but VAZ. Why? Because here Z or J. Okay. Z, dears. This has to be Z. Why? Because here J is our ground. Okay. Right. Now, what is the statement? Started A, go to Z, following KVL sign convention. Started A, go to Z, following KVL sign convention. Now tell me, what is VAZ? Start here. Plus 65, plus 65, plus 5. That is your node voltage. Now, what is the VC node voltage? Plus 55, minus 15, plus 5. What is VC? What is VC node voltage? Start here, go to ground. How much? Plus 5 volts. What is VF? Plus 15, minus 25. What is VH? Plus 35, plus 35. What is VE? Plus 10, plus 15, minus 25. Node voltage, sir. Start at that point. Go to ground following KVL sign convention. Start at that point. Go to ground following KVL sign convention. That is what the KVL third statement. Find yes, any node voltage can be easily calculated with the help of this KVL sign convention. So be perfect with this KVL second statement as well as KVL third statement, sir. Equations you can write in jet speed. Done, yes? Hope you got the point. KVL second statement, third statement, very, very, very important, sir. Very, very important. Done, sir? Right. Next, let's go with one problem and do, or let us apply this KVL sign convention on one problem. Taking sources, DS, plus, minus, resistor, and one more source here. Values our wish, sir. Values our wish. 1 volt, 2 volt. I am taking one more source here as a diagonal. Closing this with resistor. Taking one more source here. Polarity is plus, minus, and let us close this with a resistor. Okay. 1 volt, 2 volt over now. Let us take some 3 volt and 4 volt. All the resistance values as 1 ohm, 1 ohm, 1 ohm, and 1 ohm. Done, sir? I want to find other resistor voltages or voltage across the resistors. So what is the statement we have learned? Arbitrarily put two polarities, plus and minus. Started positive, go to negative following KVL sign convention. Come on. Go like this, sir. Take the path in which you know the voltages. Can I go like this? I don't know this voltage. Okay. Shortest path. Observe. Plus 3, plus 4. How much? 7 volts. Sir, voltages we are writing without putting pen, sir. Getting the point, please. Next. I want this branch voltage here. Putting plus here, minus here. Come on, go like this. Minus 1 plus 3. How much? 2 volts. Getting the point, please. Next. Let us put some polarities here. Put plus here, minus here. What is voltage? Plus 4, plus 2. How much? 6 volts. Lastly, DS, I want to find this voltage. How much? Plus 2, plus 6. How much, sir? 8 volts. 8 volts. Shall we find current through resistors? Yes, we can find. Yes. Shall we find current through resistors? Yes. Apply Ohm's law. 7 volt 1 ohm. How much current flows here? How much current? 7 amperes. Current enters at positive terminal for a resistor. Sign convention of power. What sign convention of power says? Always for a resistor, current enters at positive terminal. For a source, current enters at negative terminal. Okay, if the source is delivering power. See, elements which deliver power, current enters at negative terminal. Elements which absorb power, current enters at positive terminal. Done, sir. As apply Ohm's law here. 8 and 1. Resistor, energy dissipating element or energy delivering element? Energy dissipating element. Current enters at positive terminal. What is the current here? 8 amperes. Next, here, sir. 2, 1. What is this current, please? 2 amperes. 2 amperes. Now tell me, apply KCL here. How much current should come like this? That splits like 2 amps and 8 amps. 10 amps. 10 amps. How much current should come like this? That splits like 10 amps and 7 amps. How much? 17 amps. Next, 6 volts, 1 ohm. Let us write current in this branch. How much current will come like this, sir? 6 amperes. Now tell me, 6 amps coming like this, 8 amps coming like this. What should be this current? Addition, sir. 14 amps. 14 amps. 14 amps coming like this, 7 amps coming like this. What is this current? 21 amps. 14 plus 7, 21. Okay. Let us apply KCL here. 21 amps coming like this, entering equal leaving. Entering how much? 21. Plus, what is the entering current? 2 amps equal to, what is the leaving current? 17 amps. What is the leaving current? 6 amps. 23 equals to 23. Perfectly satisfied. We can also discuss one more question here. What is that? Using green color pen. Tell me, all resistors absorb energy. Resistors absorb power. Okay. Who is delivering power here? Come on, please. Is this source delivering power or absorbing power? Current entering at what terminal? Positive terminal. Even this source is absorbing power. Okay, sir. Next, coming, have a look into this source. Current entering at what terminal, sir? Negative terminal. This source is delivering power. This source is delivering power. Next, what about this 4 volt source? 4 volt source also delivering power. What about this source? 2 volt source. 2 volt source also delivering power. We have 4 sources here. 3 volt source delivering power. 2 volt source delivering power. 4 volt source delivering power. 3 volt source delivering power. 2 volt source delivering power. But this 1 volt source is absorbing power. Verify telling us theorem. It will be perfectly matched. Yes. Perfectly matched. Sir, how I discussed KVL with the help of additions. KVL is nothing but what? Additions only, sir. KCL, additions. KVL, additions. What we are learning in K-laws? Additions. We are learning additions, sir. This is how the approach of VEDA GATE faculties will be. We make the subject simple and easy for you, dears. We are here to make you rankers. Done, sir. Thank you. All the best.